All right. Any questions on the homework?
Yes. 1534.
All right. Say again.
1534 and 48.
We draw the circuit. All right. So 15 and 34 use the same circuit. One is finding Thevenin and one is finding Norton. The first thing to realize when you do Thevenin is what? That's gone. All right. So we're looking for the open circuit voltage between those 2 points, which is simply going to be the voltage across the inductor.
Okay. That's,
Which is pretty simple here, right?
yeah.
Okay. Because the total impedance then will basically be 3 squared plus 4 squared square root, which is 5.
Mhm.
Angle will be the inverse tangent of 1 point lots 3's. 4 divided by 3. Inverse tangent 53.1 degrees. 5 at 53.1 degrees. So this is voltage divider. So the Thevenin voltage would be the voltage being divided, 100 volts at 0 degrees, times what we wanted across, which is 4 at 90, divided by the total impedance divided, which is 5 at 53.1. So your Thevenin voltage is 80 volts at an angle of 90 minus 53.1, which is 36.9 degrees. Now, your Thevenin impedance, which is also going to be your Norton impedance for question number 34, will be, looking back in here, replacing that with a short, puts those two in parallel. So now, the Thevenin impedance would be product 3 at 0 times 4 at 90 divided by the sum, which we actually have right here, 5 at 53.1. 3 times 4 is 12, divided by 5 would be 2.4 ohms at an angle of 90 minus 53.1 or 36.9 degrees. Now for the Norton, you could take this Thevenin voltage and divide by that Thevenin impedance, or this actually circuit is pretty easy to do, because what you end up doing is what? Finding out the short circuit current right here. That's your Norton current. Oh, what is that? The short here completely takes the inductor out, and you have 100 divided by 3. So your Norton current is 33 point lots of 3's amps at 0 degrees. Make sense?
So by I and then I. Okay. Okay. Yeah. Yes.
Okay, and then 48, right?
Mhm.
Now 48 is our maximum power transfer for a different circuit. So we have 120 volts, 0 degrees, and then we have a 3, 4, and a 6. 3 ohm resistor, 4 ohm inductor, and a 6 ohm capacitor. Our load is right here. Get that right? Make sure I got all my numbers right here. Yep. Okay. So for this one, first thing we want to know is what is the load impedance to get maximum power transfer? Well, to do that, we need to know the Thevenin impedance. So to get that, remove the load, look back in here, replace that with a short. What do we have? Well, we have these two in series. So those two in series are, from our numbers over here, 5 at 53.1 degrees. And then that's in parallel to the capacitive reactance. So we do the product over the sum. Now this is going to get tricky. All right. So the product will be 5 at 53.1 degrees times 6 at minus 90 divided by the sum. Now the sum will be, I know this is in polar form, but in rectangular form, it's 3 plus J4. And then we add minus J6. So that becomes 3 minus J2. That's actually the sum that goes down there. And of course, that's in rectangular form. So when we convert that to polar form, you have the square root of 13 or 3.606. An angle of the inverse tangent of negative 2/3. -33.7. 5 times 6 is 30, divided by 3.606. Is 8.32. ohms at an angle of, let's see, 53 point. That's too many decimals. All right. So 53.1 minus 90 minus a minus, so that'll be plus 33.7. What did I get? Oh, negative 3.2. We got negative 3.2 degrees. What is the load impedance going to be? Load impedance will be 8.32 ohms, an angle of 3.2 degrees. Change the angle. That's all you need to do. Change the angle. Now, what we need next, of course, is power transferred to the load. The power transferred to the load, max, right, is equal to Thevenin voltage squared divided by 4 times RL. Essentially the load or the real portion of my load impedance. Well, we don't have the Thevenin voltage. To do that, that's the open circuit voltage across here. So again, we can use our voltage divider, 120 volts at 0 degrees, times the voltage across this device, which is 6 at minus 90, divided by the total impedance. Well, what is the total impedance? The total impedance is all these things added up, which we did there and there. So 3.606 minus 33.7 degrees, which gives us divided by 3.606. Sorry, multitasking. 1.664 times 120. Oh, sorry. Times 120. Or 199.7 volts. Now the angle will be what? Negative 90 minus the minus becomes a plus, so it'll be negative 56.3 degrees. I don't really care about the voltage, the angle. It's the magnitude of the voltage that I need. So what is RL? Well, that will be the real part of 8.32 times the cosine of 3.2 degrees. Now that's going to be like 0.99 something. It's really, really close. All right. So we take our 199.7 volts, square that, and then divide by 8.32, and the cosine of 3.32, that 3.2 degrees.
Is 8.3.
0.999. No, 998. Yeah, close enough. I get basically 4,800 watts, 4.8 kilowatts.
I'm getting 8.3, not the 0.99 for the RL.
No, this is the 0.998.
Oh, so just the cosine 3.2?
Yeah,
Okay.
times 8.32. That's the R. Okay.
Okay. Yeah.
So that's the voltage squared divided by RL gives me 4,800, and then I got to divide by 4. When I divide that by 4, I get 1.2 kilowatts. Make sense, everyone? Pretty straightforward.
I'm still not getting the same answer the way I did today.
Do you not square the voltage?
Okay, yeah.
Any other questions? All right. Moving on. Again, we skipped chapter 20 because I've been talking power the whole time. You need a nice review of that. It's all there. We get into now chapter 21. So the whole idea of chapter 21, and I've hinted at this already in terms of our series and our parallel RLC circuit. There's a special case, a magic point, if you will. What is resonance? And we're going to start with a series circuit today. I'll caveat that there. Series resonance. So what happens in a series RLC circuit? You have an inductor, you have a capacitor, you have a resistor. Now we'll come back to the resistance here in a second, but that's my circuit. We've already built this circuit. You've already done a lab on this circuit, but I didn't operate at resonance. So what we're looking at, and I've drawn this before, but I'll do it again. Inductive reactance is proportional to frequency, right? 2 pi f L. So for a fixed inductor, inductive reactance looks like that. Capacitive reactance is proportional to 1 over frequency, 1 over 2 pi fc. So for a fixed capacitance, I will have a capacitive reactance that looks like that. What we're talking, we've talked about below the resonant frequency, we've talked about above it, how the circuit will, at low frequencies, act capacitive, because the capacitive reactance is a lot bigger, and we're adding it together. So that capacitive reactance will cancel out the inductive reactance. But at high frequency, the inductive reactance dominates, cancels out the capacitive reactance, and the circuit acts inductive. So below resonance, current leads. Above, current lags. But what happens at that intersection? At this intersection, this, of course, is the resonant frequency. And that is the point when inductive reactance and capacitive reactance are equal. Given our formulas, 2 pi frequency times inductance, 1 over 2 pi frequency times capacitance, you can actually solve for frequency. So I'll divide both sides by 2 pi L. So that cancels out 2 pi L. And then I'll multiply both sides by frequency. So frequency times frequency becomes frequency squared, cancels out that frequency right there. So now by solving for frequency, take the square root of both sides. The square root of frequency squared is, of course, frequency. This is my resonant frequency. And that will be equal to square root of 1, which is 1, divided by, well, I have 2 pi and 2 pi again. So when I take the square root of 2 pi squared, I get 2 pi. And that leaves behind the square root of inductance times capacitance. That is my resonant frequency. Plain and simple, nothing else to it. So at resonance, the total impedance of this circuit is what? These two are equal.
Just R.
It is exactly R. That is correct. What is my current? Well, my current will be the applied voltage divided by R. There will still be voltage across the capacitor and voltage across the inductor because they have reactance. So the voltage across the capacitor will be whatever that current is times capacitive reactance. Likewise, voltage across the inductor will be whatever that current is times the inductive reactance. There will be voltage. Those two voltages will be what? 90 degrees one way for the capacitor, right? So my voltage across my capacitor goes to capacitive reactance. So what is the phase of the current? Let me back up real quick. What will be the phase of this current? Well, my source is at 0, resistance is at 0. The current will be at 0 degrees. You'll have no phase shift between the voltage and the current in the circuit. And so with 0 degrees current, the voltage across the capacitor will be the same as reactance minus 90. Likewise, for the inductor, plus 90. So the voltage across the capacitor and the voltage across the inductor are 180 degrees apart. So they cancel out. Sorry. Yeah, hit you. So again, this is a unique occurrence. 0 degree phase shift. In fact, when it comes to doing the lab, the easiest way to find the resonance is actually just to look at the voltage across the resistor and the voltage applied and adjust the frequency until they're in phase. That's the easiest way to do it. Now, unfortunately, the letter Q gets a little overused in this class. Up to this point, Q has been what?
A lot different things.
Well, in this class, so far, it's just been reactive power. But Q is also going to be defined as a quality factor. I think that's the word you use. Let me double check here. Quality factor. Yeah. Now, Q is specifically defined as, and we'll define this for series circuit and for parallel circuit. For parallel circuit, it gets complicated, but that's okay. You'll figure it out. So the Q of a circuit is a ratio of the reactive power. Of course, we've been calling Q all along, just to make things worse. Divided by the real power. Average power. So he says average power. What I mean is real power, or what we've been calling P. So, because this is a series circuit, because this is a series circuit, what is the same for all these devices? Current, right? Components in series have the same current. Now, when this says reactive power, it does not mean the total reactive power in the circuit, because what is that? At resonance, the total reactive power is what? It would be 0. So when we talk about the reactive power for the quality factor, we're actually talking about the reactive power of one of those components. It doesn't matter which one, right? Why? 0. No, they're not both 0. The total reactive power is 0 because they are equal and opposite of one another. So we just choose the magnitude of 1. Inductive reactance, capacitive reactance doesn't matter because why? They are equal. That's how we define resonance in the first place. Okay. So typically, and it doesn't have to be always, but generally, we use inductive reactance. All right. It can be either one, but in general, we use inductive reactance. And I say that because when we do parallel, there's going to be different. So we start with our inductor. And there's a good reason for that. We'll get to that here in just a second. So reactive power then would be current squared times the inductive reactance. The average power would be current squared times the resistance. Well, the beauty of a series circuit, of course, is what? Current is the same. So it cancels out. And so the quality factor of this circuit is the inductive reactance, and I'm going to qualify this at resonance, because we know inductive reactance changes, right? We're talking about that level right there, at resonance, divided by R. Now, this actually allows me then to play around a little bit. So, for example, the voltage across the inductor, and capacitor is going to be the same thing. Voltage across the inductor is going to be the current, which is V over R, right? V over R, times the inductive reactance. Well, inductive reactance divided by R is Q. So the voltage across the inductor actually ends up being the supply voltage times the Q of the circuit. And he puts a QS for the Q of the series circuit, because again, the parallel is just going to be all different. All right. So sometimes I put the subscript, sometimes I don't. I apologize if I don't, but it works either way. So if I have a Q of 10 and I apply 5 volts peak to peak to my circuit, that means I'm going to have 50 volts across my capacitor. Yes. And your inductor. Now, before you get all excited and say, ooh, a multiplying circuit. Nah, that's not exactly. Because as soon as you try and load it, as soon as you put anything in parallel with your capacitor, you completely change the dynamics of the circuit, and yeah, it doesn't work. Okay. But you will see a multiplying effect. For your lab, I think you apply like 4 volts peak to peak. And I think the Q of our circuit's around 2.5 or 3 or something. So you're going to get a higher voltage out than you put in when you measure. That's kind of a neat thing, right? Up to a point. Now, there are a number of other things we can do here with these formulas, all right? So, we're going to be playing with lots of formulas here. So let's explore this a little bit more. The Q factor, or I'm sorry, the quality factor. So as I said, quality factor is equal to the inductive reactance at the resonant frequency divided by R. Well, let's go ahead and plug in. So we know that the inductive reactance is 2 pi frequency times inductance. Well, we have a formula for the resonant frequency, which is where we're calculating the inductive reactance. So if we plug that in, 1 over 2 pi square root LC, all divided by R. Oh, look what happens here. 2 pi divided by 2 pi. Go on. So this leaves me with 1 over r times, so this is the tricky part. I have L divided by the square root of L. What is that? L divided by the square root of L. I'm going to multiply both sides by the square root of L divided by the square root of L. That's 1. So this gives me L times the square root of L. What do I get on the bottom? What's the square root of L times the square root of L? L. Oh, L cancels out. Oh, it is just equal to the square root of L. Okay. So, because I have L divided by the square root of L, that gives me the square root of L divided by the only thing left, square root of C. So I just put them both inside the radical. And this gives me another formula for Q. I don't even have to calculate the resonant frequency to go through all that calculation. I can just do that. Now, this shows us something very important right here. Once I have a value of inductor and capacitance, Q is also controlled by R. It's inversely proportional to R. Now, why is R important? In a circuit, when you build your circuit, you put in a resistor. Is that all the resistance in the circuit? No, it's not. What else is there?
Internal resistance.
What's that?
Internal resistance.
Of
Why?
our wire has so little resistance. I don't care about that.
Components.
Okay. Well, the resistor is resistor. But what other component has internal resistance? You've already had to deal with it. Supply. Okay, the supply does, but not that supply. This, right? The function generator. All right. See the label on there. What's it say? 100 ohms. If you have a box on there, that adds 50 to the other 50 that's already there. So you still have 100. What else has resistance? Go back to lab 3. You add an inductor. You watch that inductor current build up. And the voltage across the resistor was supposed to get to 5 volts. Didn't get there, did it? Why not? Internal resistance of the inductor. So when I go and look at this resistance here, the Q of the circuit is going to depend on whatever physical resistor you put in, plus the generator resistance, plus the winding resistance of your inductor. It all adds up. And as it adds up, what happens to the Q of the circuit? It goes down. All right. So we keep that in mind. All right. We're going to keep that in mind. Now, if you make the physical resistor big enough, then the other variations aren't going to matter that much. But you make the resistor really big, what's your Q? Nope, really small. Okay. So you can look at some of these, you can look at a simple formula like this and just say, all right, a bigger inductor, higher Q. Smaller capacitor, higher Q. So you can see that relationship fairly easily. But what do we know? We know that the bigger our inductance, the more resistance it's going to have, right? The more winding resistance it's going to have. So you kind of like fighting against yourself somewhere. So, all right. Does that make sense to everyone? Now he goes through a few other graphs here. This is kind of a fun thing to look at and think about. If we were to graph the total impedance of our circuit versus frequency, what's going to happen, right? At really low frequencies, the capacitive reactance is huge. It's going to dominate. As you approach zero, it approaches infinity. So our total impedance starts off at low frequencies really high. Then it starts to drop. And then, of course, eventually it reaches a minimum at that resonant frequency. What is that minimum impedance going to be? R. Once I get above the resonant frequency, then the inductive reactance starts to take over, and we eventually reach a point where we're doing something. What does this mean for my current? If I were to graph my current in the circuit versus frequency, if I wanted to say zero, I could just say, well, zero frequency is DC, you have no current. But then, of course, it's going to build. It's going to reach a maximum, which will just be V over R. And it will drop off. Now, for those of you in the morning class, if this is the current, and if I look at the output voltage as being the voltage across the resistor, then you take this curve of current, multiply it by R, and it becomes a voltage, but it remains the same shape. What kind of filter is that? Take this maximum. Multiply by 0.707. You actually have two intersections, a lower and an upper cutoff frequency. This is a band pass filter. Band pass filter is achieved, built, whatever word you want to use, by looking at the voltage across the resistor versus the source. Now, where does Q come in? Well, here is where, for those of you in the morning class, everything starts to come together. Q, of course, is defined for a bandpass filter as the resonant frequency divided by the bandwidth, where the bandwidth is defined as the difference between the upper and lower cutoff frequencies. So a higher Q would result in something more like this. Where those upper and lower cutoff frequencies are now closer together, resulting in a smaller bandwidth and therefore a higher Q. Make sense to everyone? It all comes together. All right, it all essentially does the same thing for us. So we're gonna define those points. We're gonna solve for all that information here. Because why not? Now I focused on the magnitude of the impedance. What about the phase shift? So a phase shift, right? So when you look at the total impedance, that's my total impedance, it's the magnitude of it. And I talked a little bit about the phase shift because the angle of the impedance will of course be the inverse tangent of the total reactance, which will basically be what? The inductive reactance minus the capacitive reactance divided by R, right? The real part. So at low frequencies, capacitive reactance is larger, resulting in an impedance that is negative. That's a negative angle. And therefore, the current will lead. Talked about that earlier. Passive, active. Above resonance, the inductive reactance is bigger, and I end up with a positive angle for my impedance, and therefore a lagging current. Well, at resonance, because those two are equal, the inverse tangent of 0 divided by R, basically the inverse tangent of 0, is 0 degrees. You have no phase shift. So if we were to look at the, I can do a graph, I guess. Phase shift, right? And this is the angle of the impedance versus frequency. Actually, I need there we go. Because I have 0 right here, right? There's 0. So the angle of the impedance starts off negative at a very low frequency. It would be minus 90. And eventually it would get to 90, theoretically. It's going to start there. Pass through 0 at the resonant frequency. And go from there. So in a way, this circuit is really acting like what? Well, it's acting a lot like a low-pass filter on one side, and a high-pass filter on the other side. In other words, the circuits you built for labs 6 and 7, okay, I'm keeping track of this, right? Okay, your RL circuit and your RC circuit, and you found something called what? What did I call that? I called it the 45-degree frequency. Why 45? Well, because it's exactly between 0 and 90, or 0 and minus 90, depending on which one it is, and whether you're working at impedance or current. Well, the same thing happens here. I will have a point where I have a minus 45-degree angle and a plus 45-degree angle of my impedance. Any guesses what those corresponding frequencies are?
Lower cutoff, upper cutoff.
Exactly. This is the lower cutoff frequency. This is the upper cutoff frequency. Because we have two places where the difference between the reactants, the magnitude of the difference between the reactances is equal to the resistance. Think about it, right? At some point, this will equal plus or minus r. And that will provide me, because the inverse tangent of 1 and -1 is 45 and -45 degrees. That is how I will actually solve for the upper and lower cutoff frequencies. It's figuring out where that happens. But it's going to be ugly. I prefer to do it one shot. So let's go ahead and take our break now. Right? So we'll take 10 minutes, come back at 10 after, and we will solve for these points. And we can use that to solve for this. And I can use all that to solve for that. So it's all going to kind of come full circle. All right, let's do some math. Now, the nice thing about all this stuff that I'm going to do, I won't ever ask you to repeat it, but we get to use the result. Okay. All right. So what we've said is we are looking for a frequency that creates a plus or minus 45-degree phase shift. That'll be my cutoff frequency. So that occurs when the capacitive reactance minus, we'll go ahead and do it the other way. Inductive reactance minus capacitor, it doesn't matter. It'll solve either way. When that magnitude equals R, that's what I'm looking for. Now, here's a very important thing that I'm going to like dual solve as we go. It's not just R, it's also what? Negative R. Okay, so I'm going to put plus or minus R on that. All right, now, what is inductive reactance? It is 2 pi frequency times inductance. What is capacitive reactance? 1 over 2 pi frequency times capacitance. And that will equal plus or minus R. So this is what I need to solve for. F, right? The frequency. This will be our cutoff frequency. All right, so how am I going to solve for this? Well, I hate fractions. Anybody else with me on that? Okay. So what I'm going to do is I'm going to multiply this whole thing by 2 pi frequency times capacitance. Because what will that do to this?
Cancel it.
And leave
Just
1. Okay. That term becomes minus 1. It's easy, right? What else? So over here we have plus or minus 2 pi f r c. Right? I just stuck the r in there. What do we end up with here? 2 pi squared. Yeah, let's just make it, let's just do it. Okay, so 2 pi times 2 pi is 4 pi squared. frequency squared. LC. Now, let's gather these terms onto one side. All right. And I'll just bring this over here. Now, keep in mind, and again, it'll be fun to play with, but when we bring something to the other side of an equal sign, becomes a negative. Well, plus or minus, the negative of that would be what?
Plus or minus.
Minus plus.
Does it change?
Yeah, it would. It's not going to make that much difference. You'll see. But anyway, I'm going to do it. So now we have 4 pi squared LC times F squared. Okay? We bring this over, becomes minus plus 2 pi RC F. Now, all I'm doing is just, I'm rearranging and I'm putting F at the end, and you'll see why here in a second. Minus 1 equals 0. What am I solving for again? No. F. Cutoff frequency. Well, what type of equation is this? What kind of equation is this? Solving for F. I have an F squared, an F, and a constant. What is that? Come on, it hasn't been that long, has it? Not exponential. Quadratic equation. You knew the answer, you're just avoiding it. You can't get away from it. I'm sorry. So when I have a quadratic equation, all right, quick review, right? A times F squared plus B times F plus C equals 0. That is a quadratic equation. What is the solution of that equation? Oh, I'm sorry. F squared. I put the 2 in the wrong place. What is the solution for that quadratic equation? You may remember? Wow. Oh. Negative b plus or minus the square root of b squared minus 4ac all divided by 2a. Been a while, apparently. Yeah. All right. Now, this is why I arranged this this way. What is this?
A.
That is A. So A is equal to 4 pi squared LC. What is B equal to?
2 pi RC.
Minus or plus 2 pi RC. And what is C equal to? Negative 1. All right. You ready? Because this is what we're going to solve. All right. Cutoff frequencies will be negative B. Well, negative B puts it back to plus or minus. All right. 2 pi RC. Plus or minus quadratic. Now, b squared. Well, b is plus or minus, but when I square it, it's always going to be positive. Okay, so when I square that, I get 4 pi squared r squared c squared. Okay, minus 4 times a, so that gives us another 4 pi squared LC. And what is C?
-1.
Minus 1. So what does this become? far, so good.
Mm-hmm.
All divided by 2 times A. Okay. Didn't make my quadratic long enough there. All right. Now, here's where it gets fun. Whew. All right, so what do we have here? Looks ugly, doesn't it? All right. So knowing where I'm going helps. Okay. But what I want to try and do is get rid of as many terms as I can. All right. So like inside here, I got pi squared, right? If I were to factor the pi squared out of both terms and then bring it out of the radical, what does it become? The square root of pi squared is pi. Okay. Now, I can do that, all right? A lot of different things I can do, all right? So if I look at under the radical, I've got the pi squared, I've got a 4 here, I've got a 4 and a 4, so I can take the square root of 4 is 2, square root of 4 squared is 4, right? So, there's ways I can get rid of some of that stuff. So just get rid of some stuff. Both of these have a C, this has a C squared, that has a C, so I can probably do something with that as well. So what I'm actually going to do is I'm going to multiply this whole thing by 1 over 2 pi C. Now, 1 over 2 pi C divided by 1 over 2 pi C is 1. All right, so I'm not changing anything. See what happens here. So up front, right, this term right here, 2 pi C divided by 2 pi C leaves plus or minus R in that first term. Now I have plus or minus. Now here is where it gets fun. So when I put 1 over 2 pi C here, when I move it into the radical, I square it, right? Because coming out of the radical, it's the square root. Going in, it gets squared. So now, under the radical, I have 4 pi squared R squared C squared divided by 4 pi squared C squared plus, what we got here? 4 times 4 pi squared LC divided by 4 pi squared C squared. So far, so good? Okay. On the bottom, I have 2 times 4 pi squared LC divided by 2 pi C. All right, you good? Now I get the red pen out. You can see where I was going. See, this is how I knew where I wanted to go. But what happens in here? 4 pi squared, C squared, C squared. Okay. This term, 4 pi squared, pi squared. Now, C divided by C squared, what happens there?
You just have you just have a 1 C on the bottom.
Exactly. So what happens is I just basically take one of these, cancels out that. All right. What happens down here? Well, the 2 cancels the 2. Pi squared divided by pi cancels out one of those. And then the C cancels the C. All right, so what does that leave me? Leaves me a lot less. That's a lot of cancellations, right? All right, so I have plus or minus R. Plus or minus the square root of, what's left here?
R squared
R squared
plus 4L
plus 4
L over
L over C.
all over 4 pi L.
All divided by
4 pi L.
4 pi L. Wow. That really reduced, didn't it?
Mm-hmm.
Quite a bit. All right. So let's go ahead and write that again. And then look at the possibilities. I need room to work here. Because then we're going to use it to do some other solutions. All right, so we have, where are we at? What we have is our cutoff frequency is equal to plus or minus R plus or minus the square root of R squared plus 4 times L over C. I'll write it like that, a little easier to read. All divided by 4 pi L. Now, how many different numbers is that going to be? How many different solutions is that? 4. But what is nonsensical? Any negative result. So, what will the number under the radical be? It will be R, the square root of R squared plus something.
It has to be positive.
Which means it will always be greater than R. Right? Does everybody see that? This term right here will always be greater than R. So, one solution that works is plus R plus that. Because that's going to be a positive number. What is one that won't work? Negative R minus that. That's always going to be negative. The other one that will be negative is plus R minus something greater than R. So the other one that works will be negative R plus something greater than R. Which means what? If you weren't paying attention, this is always positive. So that minus sign goes away. And so I'm going to rearrange this equation to make it a little bit more doable in terms of doing the calculations. And that'll be, we're going to put this up front because it's always positive. And then we'll put the plus and minus R back here. And then divide by 4 pi L. So that is, or those are my 2 cutoff frequencies. Now, think back, for those of you in the morning class. What is the resonant frequency? I did this a while back. Or no, I did this last week for you guys in the morning class. Actually finding the center resonant frequency is done by taking the square root of the product of the upper and lower cutoff frequencies. That is the exact formula for a resonant frequency. Well, let's do that. I am saying that the resonant and center frequency, we'll just call it the same thing, will be equal to Now, the lower cutoff frequency will be the smaller of this, which will be the minus. The upper cutoff will be the bigger one, which will be plus R. Doesn't matter when we're multiplying together. Now, I'm going to keep this simple. So we're going to take the square root of F1, lower cutoff frequency. Now, I'm not going to write all the stuff in the radical. I'm just going to say the radical, okay, minus R divided by 4 pi L. That's F1. Times F2, which is the radical, plus R divided by 4 pi L. Okay. Now, there's a reason I'm doing that. Okay. So what am I actually going to get here? First off, 4 pi L times 4 pi L, the square root of that is 4 pi L. Right? Now, what happens up top? Well, up top, we have to use FOIL. So we're going to take the first, which is the radical times the radical, which is what's inside the radical. So all of that, this times that, becomes R squared plus 4 times L over C. That's the first. Now, outside and inside, what happens? The outside is the radical times R. The inside is the radical times negative R. What are those two going to do? They are going to cancel. Right? Everyone got that? It's going to cancel. Okay? So that leaves the last, which is minus R times plus R, which is minus R squared. Okay? And then I have to take the square root of all that. Now, here I have R squared minus R squared. Cancels out. Something's missing. Something's wrong. Come on. Oh, I already took the square root of the bottom. Sorry. Right. Okay. There we go. I knew something's wrong, not quite right there. That's what I did, right? So I mean, if you want, we can extend the radical and just put 4 pi L squared there, but I already took the square root. Okay? Make sense so far? All right. So what does that leave? Well, that means that center frequency will be, so the square root of 4 is 2. And then I have the square root of L over C divided by 4 pi L. So divide top and bottom by 2. 2 goes away, 4 becomes 2. I'm going to rewrite this as the square root of L divided by 2 pi L square root of C. Well, we already learned something, right? If I take and divide the top and the bottom by the square root of L divided by the square root of L is the square root of L. Square root of L divided by the square root of L is 1, and I end up with 1 over 2 pi square root of L and square root of C.
Oh wow, back here. What a
Whoa, right? Mind blown yet?
seems so incredibly unnecessary. Seems so long.
You're not wrong.
All right. But wait, there's more. All right, so that looks pretty good proof to me, right? What's the bandwidth? Bandwidth is upper cutoff frequency minus the lower cutoff frequency. So my upper cutoff frequency is the radical. Upper cutoff frequency is that one. So it's the radical plus R divided by 4 pi L minus the radical minus R divided by 4 pi L. Well, again, why did I just write radical? So both of these have the same common denominator, 4 pi L. And when I take the radical minus the radical, it's gone. And then I have R minus a minus R becomes plus R. And I end up with,
which then turns to R over 2 pi L.
so this becomes R divided by 2, right? So that cancels to a 2 pi L. Now, you're like, where do we have that formula? Or do we? We actually don't, right? We haven't.
Now
But,
two.
but, what do we know? We do have the fact that Q is equal to the resonant frequency divided by the bandwidth. Which means the bandwidth is equal to the resonant frequency divided by Q. Divide both sides by Q, divide both or multiply both sides by the bandwidth. We just swap that relationship. Well, we haven't really done anything with this, have we? Oh wait, we do have a formula for Q. Anybody remember the formula for Q?
Yes. This is a
What's that?
you give us a way to get Q, and now this would be
So Q
would be
is calculated by taking the inductive reactance divided by R,
oh yeah.
right? And that's the inductive reactance at resonant frequency. Okay, so that would be 2 pi resonant frequency times inductance divided by R. So now, I take the bandwidth, I take the resonant frequency divided by Q, which is 2 pi resonant frequency L divided by R, which becomes, when I flip that, R, oh, resonant frequency cancels, so it's just R divided by 2 pi L. Oh, what do you know? Oh, I'm sorry, that actually, I wasn't solving for Q,
That's B.
I was solving for the bandwidth, sorry.
Yes, and now
Got ahead of
we get to
myself. There we
Q. I
Right.
know.
And there you go,
We're not solving.
identical formulas. There's other ways I could have done that.
That means Q also equals square root of L over R times square root of
1 over R squared of L over C.
Yes.
Yes, that's another way to do it. That was a little uglier, but you get the same result. Maybe we could do it real quick, right? So Q is also equal to 1 over R squared of L over C. So if we solve for bandwidth, we're going to take the resonant frequency, which is 1 over 2 pi square root of LC, and divide by 1 over R square root of L over square root of C. So when you do that, what do you get? All right. So you end up with, on the bottom, 2 pi. And then in the denominator, you have 1 over R, so R ends up here. And the hard part is here. All right. So what I'm going to do here is I'm going to multiply the top and the bottom by the square root of LC. Okay. Which up top becomes LC. And on the bottom becomes square root of L times square root of L ends up being L. Wait a minute, what am I? 2 pi. First C. Oh, no, sorry, my bad. Square root of LC is on the bottom. So when I multiply, we move that up a little bit. So I have square root of LC divided by square root of LC, which becomes 1. Okay. Here, I have the square root of L times the square root of L becomes L. Here I have the square root of C divided by the square root of C, which cancels. And then I just same answer. How many different ways did we get there? 3 different ways to get there. Okay.
584.
What's that?
584. The methods that I'm seeing.
All right. Questions on all this? We came up with a real complicated formula, but it turns out that it can simplify quite a bit. And we can use that formula to calculate you know what, I think I forgot to print out in the lab, which I think is two-sided, unfortunately. Too many tabs open again. This is lab 13. Resonant series R, oops. Resonant series RLC circuit. And yep, it is 2 pages. So let me go ahead. I'm going to send this to my double-sided printer. I'll go ahead and get the projector warming up here so we can talk a little bit about this lab. All right. I'll be right back.
No, hard. Let's do it, man. But I know what she said it's there. Like exactly, so what? I want to know. You got the answers? Killed you.
Okay, thank you for your patience. Here you go.
Before anyone forgets, remember this is double sided.
All right, so you are going to build a series RLC circuit. Apply 4 volts peak to peak, and a 1.2 k ohm resistor, 100 mH inductor, and a 0.01 microfarad capacitor. Now, even though I don't ask you to predict the resonant frequency, let's go ahead and do it real quick. So we're going to have 0.1 henries times 0.01 microfarads. You take the square root of that, multiply by 2, multiply by pi, and then take the inverse, right around 5,000 hertz. So if you build a circuit and you find a resonant point and you're not close to that, something's wrong. Okay. I like to give you that information so you know what to expect. Right? Oh no, actually I do tell you to calculate it. Oh, never mind. I just did step 2 for you. Well, part of step 2. Okay. And I think I told you that just so that you would be able to, get close to it. So set it near it, and then watch the voltage across the resistor and look for that 0 phase shift. All right, because when that phase shift is 0, you're good. That is resonance. Then you're going to take and determine what that frequency is off the dial as best you can, probably as accurate as you need. And you're going to measure the voltage across the resistor, the capacitor, and the inductor, which means, right, as you learned from lab 8, where you did this same circuit, different, might have been a different capacitor value. You're going to have to move the components around to measure. That's probably the easiest way to do it, right? If you just use wires, plug it in, and then just move the component you want to measure. And at the end, you're actually going to then go ahead and measure the voltage across both the capacitor and the inductor. So they're in series, so you'll just basically measure across the two of them. Now, in the ideal world, what would that voltage be? In the ideal world, what would the voltage be across the combined capacitor and inductor? It would be 0 in the ideal world, where, of course, we do not live. All right? Why will it not be 0 in the real world?
Because 0 is ideal, and the real world is an ideal.
But why? There's a very specific reason why. And we're going to actually deal with that reason a whole lot more next week.
Because components have resistance.
Well, specifically, the inductor. Capacitors, especially our small mylar capacitors, are really close to ideal. They act very ideal. Inductors, not so much. That's really where most of the problem is, because I can't make an inductor, especially a lot of inductors, without lots and lots of small wire wound around to create the inductor, and thus giving me some amount of resistance. Anybody remember what the resistance is of your 100 millihenry inductor? The fact that you got about half a volt across it lost half a volt out of 5, would indicate that it is somewhere close to roughly 1/10 to 1/11 of what the resistor value was. That was a 1K resistor, so you're talking about 100 ohms of resistance. Realistic. That's what you're going to have. Right? Now, at resonance, all right, at resonance, and we can go ahead and come back here, all right, real quick. Take that resonant frequency, multiply it by 2 and pi, and the inductance, 0.1, to find out that at resonance, we have a reactance of about 3.16K. Now, what is the significance of that? That is the inductive reactance. You divide that by R, and that gives you the Q of the circuit. Now, the R in the circuit is a 1.2K ohm resistor, but what did we just say? Oh, there's another 100 ohms in my inductor. Oh, and there's another 100 ohms in my function generator. So the Q that I actually end up with is going to be that reactance divided by 1400. Or a Q of about 2.26, roughly. Which means when I put in 4 volts peak to peak, I'm going to see at least 9 volts out. And you might even see a little bit more because the interaction of the resistance from the function generator is not always really that much. So maybe the Q is a little higher, maybe you get a little bit more than 9 volts. But you should get about 9 volts. And because you set the phase shift to 0 degrees, you should see a nice, perfect, negative 90-degree phase shift across your capacitor. But that's where the inductor comes into play. Because now, yeah, the voltage across the inductor is not going to be quite that. Because what we actually have for the inductor will be what? We've already determined that the inductive reactance itself was 3162, whatever it was. Back here somewhere. 3162. And of course, the winding resistance is 100 ohms. So the actual reactance of the inductor becomes 100 plus J 3162. That's what you're actually going to have. So because of that, obviously 3162 squared plus 100 squared, you take the square root, is a whopping 3164. So the magnitude is almost exactly the same. The angle, 3162, divided by 100, take the inverse tangent of that, and you get about 88 degrees. So the reality is, what is 3164 at 88 degrees. So you should see pretty close to 90, but it might be off. And of course, at resonance, when you go to look across the inductor and the capacitor combined, when you add up the capacitive reactance, which is minus J 3162, you're going to have, when you add those two together, about 100 ohms. So whatever current we have, right, if we have 4 volts peak to peak, and we have a total resistance of about 1.3 kilo ohms, you multiply that by 100 ohms, you're gonna have a little less than 1/10 of 4. So you're gonna have around a third of a volt, just rounding my numbers. So you will see some voltage. And check the phase angle. Phase angle should be 30 close. You know, if you're off a little bit, it doesn't take much of a not quite exactly zero reactance to make that. When you're working with 100 ohms, if you're off by 100, that's a 45 reactance. So depending on how good you get it, see how close you get. All right. That might even, to find the perfect resonance, might even be better to look at across XL and XC. Find that 0 degree phase. But anyway, so that's what you're going to see initially. What you're going to do then is go through and change R. So you've actually got all the data you have for here. All right. So your voltage at resonance across the resistor ideally would be 4 volts peak to peak. We know it's going to be a little bit less because of the inductor. So you might see 3.6, 3.7, something like that. All right. That shouldn't change at all. Should pretty much be pretty consistent as I change my resistor. Then you're going to find the upper and lower cutoff frequencies. Now, how are you going to do that? For those of you that have already taken 125, oh wait, no, we didn't do it 125. For those of you in the morning class, this was experiment number 37. How'd you find it? Well, you take whatever your voltage is at resonance across the resistor, 3.6 volts peak to peak, 3.55, whatever it is, you multiply it by 0.707. Because that is what you're going to see at the cutoff frequencies. So what you're going to do then is you're going to figure out what that voltage is. You're going to lower the frequency until you get to that peak to peak. That's your lower cutoff frequency. You're going to raise it until you get, it's going to go back up and it's going back down again. And when you get down to 0.707 of that maximum voltage, that's your upper cutoff frequency. Make sense to everyone? So you're going to measure those two, and then you're just going to subtract the difference. That will be your bandwidth. And then you'll take that resonant frequency, you got 5, whatever, divide by the bandwidth, and that'll be your Q. Now, let's do the predicted Q for the 1200, right? I'll just go through that example for the 1.2 k ohm resistor. And there's a number of ways that we can do these, right? My predicted upper and lower cutoff frequencies. So the lower cutoff frequency will be R, square root of R squared plus 4 times L over C plus, for the lower it'll be minus R divided by 4 pi L. Now, realistically, we'll go ahead and let's just use the resistance of the inductor plus our resistor. So that'll be 1300 squared plus 4 times L, which is 0.1, divided by C, which is 0.01 times 10 to the negative 6, minus R, which is 1300, divided by 4 pi L, which is 0.1. So I'm going to do this on the calculator. I'm going to do that first, add that, take the square root, subtract that, and then divide. Easiest way to avoid having to store information. Calculator back up here. All right, so we're going to take 4 times 0.1 divided by 0.01 times 10 to the negative 6 equals, that's 40 million. I'm going to remember that number because I have to use it again. Okay, and I'm going to add 1300 squared. Take the square root of that, subtract 1300. Oops. I don't know why that one just sometimes doesn't want to work. Okay. And then divide that by 4 pi 0.1. So that gives me a lower cutoff frequency of 4104. The upper cutoff frequency will be all of that plus R. Okay, so I'm not going to rewrite the whole thing. So if you recall, we had 40 million plus R squared. I should have actually remembered that number because I should have remembered the square root of that, but that's a little harder. Plus 1300 squared. Take the square root. Square root. Yeah. This time we're going to add 1300. So really, oops, did it again. So really the radical is going to be the same both times. So you can put that in storage and just reuse it. And then I'm going to divide that by 4 pi L. Whoop, I messed something up. What did I mess up? Shoot. All right, let's try again. Square root plus. Oh, I know what I did. I didn't hit the equals. I got the equals. Now divide by 4 pi L. There we go. 6173. 6173. So that gives me a bandwidth predicted of 6173 minus 4104, or about 2069 hertz, which gives me a predicted Q of 5032 hertz was my resonant frequency, divided by 2069 is really, really close to about 2.5, probably about 2.49. Remember earlier when I did the Q, I'd say it was about, what did I say it was? 2.33, I think. But that was when I used 1400 for R instead of 13. So anyway, but there you go. All right, that's all your predictions. Questions? A little less math this time, right? At least no trade.
And how dare you say less math, especially after
Hey,
all
it's
the
algebra. Which would you rather have? Trig or algebra? Come on. What's that? There you go. Who's saying trig? Yeah,
Become a mathematician instead.
What's
Because
that?
become a mathematician instead, you get all the trigonometry you could ever want. All the numbers, all the confusion.
So much fun. All right. So I think I'm pretty much, and when you look at the formula in the book, he writes it a little bit differently. You get the same results. He just simplified it differently. I think mine looks better than his, personally. All right, which is why I do that. All right. Questions on all this? I did a lot of algebra, right? But the final formulas are pretty simple. Pretty simple. And we start with series resonance because it is simple. And the reason it is simpler is because it is series. When you get to parallel, which is what we're going to do next week, it gets a little ugly. All right? Why? The thing that makes it ugly is that winding resistance. It's a little bit more complicated as a result. All right, so for homework, this is week 12. I should have just gone to that. Yeah, whatever. Right, come on, you can open. You can open. Faster to just download and open. All right. Out of chapter 21, problems 2, 6, and 8. Two, 6, and 8.
No,
You got lab 13. Now, next week, we're gonna have another quiz.
Yes.
This quiz is on RLC circuits. What is that? Quiz number 5?
6.
6. Quiz number 6. Wow.
Rolling.
Okay. So you got a chance at what? Series, or parallel, or maybe both. All right. And we are going to cover parallel resonance. So we're still in chapter 21, but now we're in a slightly different variation. Questions? Hey, you're done early. Cool. Make up for this morning.
Except
All
you
right.
were late this morning.
Was that?
You were late this morning by like an hour and a half.